Hi guys, in this video we're going to revise mechanisms from the AS and the A2 syllabus, and this video is suitable for students in the second year of A-level chemistry, so A2 students. You can find this past paper question pack in the link in the description below. This first question is asking what is meant by a sigma bond and a pi bond. So this is from AS, the first bit of the organic module. A sigma bond is the overlap of orbitals between two bonding atoms, and a pi bond is specifically the sideways overlap of p orbitals. So here I've drawn how a pi bond is formed from the sideways overlap of p orbitals. These are the p orbitals on each carbon atom, and here is the electron density where the p orbitals have overlapped above and below the plane of carbon atoms, and this bond here is the sigma bond and this is the pi bond. Next question asks how many sigma and pi bonds are in one molecule of buta-1,3-diene. So to answer this question, I've drawn the molecule below, and then all of the single bonds are sigma bonds, so I've counted all of these. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9 sigma bonds, and the double bonds, each single part of the double bond is a pi bond, so 1, 2 pi bonds in this molecule. The next question is also about AS content. It's something called Markovnikov's rule, and that states that when we have an unsymmetrical alkene, we can get two different isomeric products formed. So the next question is about Markovnikov's rule, and that is when we have an unsymmetrical alkene and we react it with hydrogen bromide, we can get a mixture of two different isomeric products, because the hydrogen and the bromine can be on either side of this carbon-carbon bond. So this carbon-carbon double bond turns into a carbon-carbon single bond, and the hydrogen and bromine can be on either side. And the major product is formed through the most stable carbocation intermediate. And you have to remember that tertiary carbocations are the most stable, then secondary, and then primary carbocations are the least stable. And we identify the type of carbocation by the number of carbon groups it has around it. So looking at this answer first, it wants the mechanism showing the formation of the major product, which is going to be formed through a secondary carbocation. We've got the electrons. A pair of electrons comes from the double bond, so that double bond is going to turn into a single bond. We're going to form a bond to this hydrogen, which becomes this bond here. The HBr bond breaks, so we end up with Br minus. Then we have our carbocation intermediate. A bromide ion acts as a nucleophile and attacks this positive carbon of the carbocation, and it forms a bond to produce our product. Now this carbocation intermediate is secondary because we have two carbon groups. We have the CH3 here and the CH2CH3 here. Two groups secondary. If the bromine bonded here, then it would be formed via a primary carbocation because it's surrounded by just one carbon group. This next question is testing your knowledge of curly arrow mechanisms and applying it to an unfamiliar example. So the Diels-Alder reaction is not on most A-level specifications. It is university level organic chemistry. So in this reaction we have a diene, that's just an alkene, so two double bonds. We've got something called a dienophile, so something that's attracted to that diene, that alkene, and it results in the formation of a new six-membered ring. And the question, the first part of it says add curly arrows to the diagram below to complete the mechanism for this reaction. So we've got our two starting things, and we want to form this 6-membered ring. So we can see that we need a double bond here, and the other double bonds all disappear. So we've just got single bonds around this 6-membered ring. So in order to get this double bond can just move here. So each arrow is the movement of a pair of electrons. This one, the electrons from the double bond move here to form a single bond, and it leaves behind a single bond. And electrons from this double bond move here to form a single bond here. And we end up with this 6-membered ring with one double bond over here. Then there's 2 more of this type of reaction, and it wants us to draw the product of each reaction. We don't have to do the curly arrows, but I've done them just so I could work out and see what was formed. So it's the same thing again. The electrons from the dienophile are going to move down here to form a single bond. These are going to move up here, which causes these to move up here. So we have a 6-membered ring formed here, and we end up with this. And then exactly the same thing going on here as well. These look different to what's up here, but it's the same movement of electrons each time. And then this is quite funny looking, but it might be easier to draw it like this. This is just this. This next question is about free radical substitution from AS Chemistry, and it's asking for the initiation and propagation steps for the reaction of hydrocarbon A, and it gives us the formula, the structural formula, with bromine. So the initiation step, that is the halogen generating the radicals. And then the propagation steps, it's always the same pattern. So we've got the hydrocarbon reacting with a halogen radical to give us an alkyl radical and the hydrogen halide. And then we have that same alkyl radical reacting with another molecule of the halogen to produce the haloalkane and a halogen radical. Then it asks us for 2 limitations of radical substitution in organic synthesis. So limitation is we want to control our synthesis, so a mixture of products are formed, and that's because further substitution can occur. So we won't just get this mono-substituted product here. We could get another bromine attached here and another one here. The bromine can replace any hydrogen in that hydrocarbon. And the substitution can happen at different points or positions along the carbon chain. So we might want it in a specific place, but it can happen anywhere. The next question, we've got compound F here, and it's reacting with hydrogen cyanide using sodium cyanide in solution and aqueous hydrogen ions. And it's asking us for the mechanism. So the nucleophile is the cyanide ion, and the electrons come from the lone pair and attack that delta positive carbon on this carbonyl here. Then the electrons go from the carbon-oxygen double bond onto the oxygen, which forms this intermediate with the negative charge on the oxygen. The electrons then go from the oxygen lone pair and to a hydrogen ion in solution, and that forms the alcohol functional group. And our product is a hydroxynitrile. The mechanism is nucleophilic addition. We have our nucleophile here, and it's adding onto this molecule. Explain why the mechanism involves heterolytic fission. So it's heterolytic because one of the atoms receives both the electrons, and fission, a covalent bond, is broken. We've got another mechanism here. We've got 3-methyl-but-2-enol, and it's reacted with hydrogen bromide. So that's an electrophilic addition. And this reaction is from AS. So the electrons come from the double bond and move to this delta positive hydrogen on the hydrogen bromide. That causes the HBr bond to break, and those electrons from the bond go onto the bromine to form a bromide ion. That bromide ion then attacks the positive carbon in the carbocation intermediate, and we form our product. Explain why one of the organic products forms in a much greater quantity than the other. So the one that we get more of, the major product, is formed through the most stable carbocation intermediate. So the most stable intermediate, this one, is a tertiary carbocation, because our positive carbon here is surrounded by 1, 2, 3 alkyl groups, so it's a tertiary carbocation. The next question, we've got methylbenzene, and it's reacting with sulfur trioxide to form this structure here. The electrophile in this reaction is SO3. Complete the mechanism for the formation of this. So in this mechanism, the electrons are going to come from the benzene ring onto the delta positive sulfur, and that causes the SO double bond to break, where the electrons move onto the oxygen, forming this negatively charged oxygen in the intermediate. Since the electrons have come from the ring's now broken. So one of the hydrogen atoms here, this bond is going to break, and the electrons from that carbon-hydrogen bond are going to move into the ring to reform that ring. In this final question, it's about benzene compounds again, and it says outline the mechanism for nitration of benzoic acid, and it's asking us to show how sulfuric acid behaves as a catalyst. So first we have to show, for 5 marks, the generation of the NO2 plus electrophile, so how the electrophile is formed. We have a mixture of 2 acids, and that forms NO2 plus the electrophile, HSO4 minus, and water. That's our first mark. Then the mechanism, the electrons come from the ring and to the NO2 plus electrophile. We form this broken ring structure again, and the electrons come from the carbon-hydrogen bond to that positive charge to reform the ring. And here we have our product, and H plus formed as well, which came from here. For the final mark, we need to show how the catalyst is regenerated. So the H plus that was formed here reacts with this HSO4 minus, and we reform our sulfuric acid catalyst.